Hi ladies, this is lesson 7.4. So this lesson is about corresponding parts of similar triangles. So earlier this chapter we looked at proving triangles were similar, or showing that triangles are similar based on either side, 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 and those sides are all proportional, or side, angle, side, where the sides are proportional and the angles are congruent, or we had two angles that were congruent. Now we're going to look at other special segments of corresponding parts within the triangle, and if they're similar, what's true about those other special segments. So just to start off, we have a few key vocabulary terms, and these are not new terms, these are terms that you've used before. And the first one is the median. And a median of a triangle, if you remember back to, I think it was about chapter 4, the median connects the vertex to the midpoint of the opposite side. So let's look at this triangle, for example. So on this triangle, if we're looking for the median, our segment is going to go from any vertex to the opposite side. So if this is the vertex, and this is the median of the opposite side, that means that these two segments are congruent. Now our next term is midsegment, and again this is a key vocab term from that same chapter. And a midsegment connects the midpoint to a midpoint. So from one side to another, the midpoints are being connected. Now we have a couple special conjectures about midpoints or midsegments in triangles. One is that they're parallel, and secondly that a midsegment is half the length of the third side. And that was from earlier this chapter, or earlier this semester rather. So if this is our triangle, we're looking at a midsegment or a midpoint and connecting it to another midpoint. So that means this side and this side are congruent, and then also that those second two segments are congruent. So that's midsegment to midpoint to midpoint, that's midsegment. Now let's look at the altitude. The altitude of a triangle comes from the vertex and is perpendicular to the opposite side. So if this is our triangle, our altitude would be perpendicular to the opposite side of the vertex. And then lastly we have angle bisector, and an angle bisector divides an angle into two congruent angles. So this segment, our angle bisector, that's going to give this angle and this angle congruent measures. So those are our review vocab terms. Now in the next part on your note sheets you have a box and it says to draw a scalene triangle. So please draw a scalene triangle in that box, and I want you also to measure each side of your triangle. So you can pause the video while you work and unpause, and we'll work through the properties of those special segments. So here's my scalene triangle. Now what you need to do is choose a scale factor, and you can choose any one of these. If you drew a really large triangle, you may want to use a small scale, and if you drew a smaller triangle, you may want to use a larger scale. I'm just going to use a scale of 2, and you need to draw a similar triangle in that second box. So in the box below, draw a similar triangle. Now there's a few ways you can draw a similar triangle. You can either make all the angles congruent, so you could use angle, angle. You could make all the sides so they're corresponding, or you could use side angle side. Probably for this lesson, this is probably the easiest to construct a similar triangle, because to do that, you're going to measure one of the sides or one of the angles of your triangle. So I suggest you use side angle side to construct a similar triangle, just because it'll give you the least amount of errors. So you should measure one of your angles, and then with that angle, so minus 53 degrees, so with that angle, extend the sides of your triangles so that they are the scale that you want, because the angles are going to all stay congruent in a similar triangle, but it's the sides that are going to change proportionally. So if, for example, you're using a scale factor of 3, you would extend this side until it's 3 inches. And then you would extend this side until it's 6 inches. So you're going to multiply your sides by your scale factor. So again, I chose a scale factor of 2, so now my sides, all my angles are the same, but my sides are all twice as long in my larger triangle than they are in my smaller triangle. So now what you should do is I want you to draw the altitudes, the corresponding altitudes, medians, and angle bisectors. So make sure your altitude in both triangles comes from the same angle. Your medians should connect similar sides, and your angle bisectors should come from the similar angles. And then you should measure with your ruler, measure each of those distances in the small triangle and in the large triangle. So I started with my altitude, and each of my altitude comes from this top angle. And when I measured them, my first altitude in my small triangle was 0.75 inches, or 3/4 of an inch, and then my larger altitude was 1.5 inches. The green segment, those are my medians, so they come from my right angle. You can do this all from the same angle if you want, but I just chose to do these from different angles so that you could see a little more clearly what they are. So the median comes from the angle on the right, and when I measure that in my small triangle is 1 3/4 inches. When I measured it in my large triangle, it was 3.5 inches. And then lastly, I did my angle bisector, and that's the red segment that you can see. So it comes from my bottom left angle, that 53-degree angle. And in my small triangle, it's 1.25 inches, and in my large triangle, it's 2.5 inches. And all of these measurements I just got from using just a ruler on the note sheet. So you'll have to draw the segments and then use a ruler to measure the length of those segments. So for the angle bisector, you'll have to actually measure the angle and divide by 2 in order to draw that segment. And then with your ruler, measure how long the segment is. If you look at the next question on your note sheet, it's how do the lengths of these segments compare? Well, they are all the same ratio. So the small triangle has an altitude of 0.75 inches compared to the large triangle at 1.5 inches. If you set these all up as ratios, they would all be equal. 0.75 to 1.5 equals 1.75 to 3.5, and that equals 1.25 to 2.5. So that means that all of these corresponding altitudes, all the corresponding medians, and all the corresponding angle bisectors are all proportional. So again, all of our ratios are equivalent, therefore all of our segments are proportional. Now the next question is, do you notice a relationship between the lengths of the scale factor of your triangles? Well, in order to get from my small triangle to my large triangle, I multiplied by 2. And here, for my altitude, in order to get my altitude from my small triangle to my large triangle, I multiplied by 2. For my median, from my small triangle to my large triangle, I had to multiply by 2. And lastly, for my angle bisector length in my small triangle to my angle bisector length in my large triangle, I had to multiply by 2. So yes, the same scale is applied. So our conjecture here, our proportional parts conjecture, if two triangles are similar, then the lengths of the corresponding altitudes, medians, and angle bisectors are proportional. Now in this next part, this next conjecture that we're going to look at, this is the angle bisector to opposite side ratio. So we're looking at our angle bisector, and then we're looking at the opposite side. So it's not necessarily true that an angle bisector is going to be the median. It's only going to be the median if it's an isosceles triangle. So we're going to work with the scalene triangle that we've been using. So on your note sheet, I want you to measure those two segments that the angle bisector creates. So in the small one, here's one segment, and here's another segment. So the angle bisector divides that opposite side into two different pieces. So I want you to measure both of those pieces. And when I measured mine in my small triangle, I got 0.5 for my shorter segment and 1 for the longer segment, and that makes up that 1.5 inch side. In my larger triangle, I got 1 inch for the shorter segment and 2 inches for the larger segment, and that makes up that 3 inch side. So if we look at that ratio, the angle bisector to the opposite side ratio. So my angle bisector or the angle that my bisector, that red line bisects, is formed by a 1 inch side and a 2 inch side. So let's look at that ratio. 1 inch to 2 inches. And then the segment, the third segment, is cut into two pieces, a 0.5 inch piece and a 1 inch piece. So if you look at this ratio, 1 to 2 is the same as 0.5 to 1. So those two ratios are equivalent. Now if we think about our large triangle, let's look at the same ratio, the angle bisector to the opposite side ratio. This angle, this whole angle, is made up by a 2 inch side and a 4 inch side. And it cuts that third side into a 1 inch side and a 2 inch side. So the segments that form the angle have the same ratio as the split segment, the third side. So this angle that's being bisected has a 2 inch side and it has a 4 inch side. And the angle bisector cuts that third side into a 1 inch piece and a 2 inch piece. So our next conjecture It says an angle bisector of an angle in a triangle. It divides the opposite side into two segments whose lengths are in the same ratio as the length of the two sides that form the angle. Or the angle that's being bisected. So let's use that last conjecture to solve this problem. So here are the two sides, 16 to 8. That ratio is going to be the same as the two segments that are formed by the bisector. So that's going to be the same ratio as 11 to x. So when we multiply this out, we get 88 equals 16x. And then 88 divided by 16 to solve for x is 5.5. So this segment here, x, is equal to 5.5 meters. And then this last problem, you can take a minute to read through it, but is similar to the problems using similar triangles that we did in the last lesson. So Holly was visiting Chicago. She saw the Willis Tower. She wanted to measure the height of it. She decided to use a 12-foot light pole to do an indirect measurement. So here's her light pole. And at 1 o'clock, the shadow was only 2 feet long. So then she looked at the shadow of the Willis Tower. So here's the Willis Tower, and here's the shadow. And she measured the shadow, and the shadow of the Willis Tower was 242 feet. So what she's wondering is, how tall is the Willis Tower? So we need to set up a proportion for this. So again, a couple different ways you can do it. I usually use the corresponding sides, always set those equal. So the height of the tower compared to the height of the light post, that's going to be equal to the shadow of the tower compared to the shadow of the light post. And if we multiply that out, 12 times 242 is 2904. And then we need to divide that by 2 in order to solve for x. And we get 1452. So this is her estimate that the Willis Tower is approximately 1,452 feet. Now the actual height, if you look it up, is 1,450 feet. So using this method, she's pretty close, just using proportional triangles. So your assignment for this lesson is written on your note sheet. So if you have any questions, please ask and bring those questions with you to class next time I see you. Thank you.